All right. So thank you, everybody. And I will be presenting our work classification by attention, seeing ref classification with prior knowledge. This was a work with Sina Bahalu and Volker Tress at the Ludwig Maximilian University of Munich as part of my PhD, and it was presented at the AAAI conference this year, 2021. So I will be talking about common sense in computer vision. And first, I will have to describe the setting that we're going to talk about, which is seeing graph classification. Seeing graph classification is basically about classifying objects and their relations in images. So typically, you're familiar with normal object classification, but in seeing graph classification, given an image such as the one here on the top right, we extract a graph that like a structured form that describes the image, like such as the man and riding a bike and a bottle on the sidewalk and so on. What we study in this work is the role of common sense in scene understanding and whether we can use some form of mental images, which I'm using as terminology, general terminology here, of our symbolic knowledge instead of the real images as training data. By common sense here, I'm specifically talking about a form of knowledge which we represent as triples, such as a person rides a horse. Note that this is different than the image itself. This is not dependent to the image. This is really symbol-based, like typical knowledge. Some people sometimes call it a world knowledge, semantic knowledge, symbolic knowledge, or sometimes just in a general form in psychology, it's called prior knowledge. I will first talk about common sense in inference, which means, for example, we are given an input image such as the one here. I assume you're seeing my cursor. I'm pretty sure you do because yeah. And then we extract the bounding boxes and the context and the representations using a convolutional neural network, for example. We can contextualize the representations using message propagation with graph convolutions or transformer or RNN. In this work, we use a graph transformer, and then we can classify the entities. So here, for example, at first, we classify the fruits, the red bounding box, and the oranges. But because we can see the basket or the ball in this image is it doesn't have enough like visual features, really, it's hard to classify. Therefore, at first, it might seem unknown. However, given the fact that we have already detected fruits and oranges, if we take a look at the prior knowledge or the common sense, we know that typically fruits and oranges go into bowls or baskets, and we can use this form of prior knowledge to further enrich our classification of the scene. As you can see here, once we have the initial classification, we can take a look at the prior knowledge. Prior knowledge can tell us this fact. It's important to notice that the prior knowledge can also tell us that the fruits can be on the trees. So therefore, we need another step where we actually combine the representations from the prior knowledge with the image again. So the image can here help us to know that this is actually the fruits in the basket rather than the fruits on the tree. And in the second part of the talk, I will be talking about common sense in training, which means given this architecture that I just described, it might be possible that we can improve the classification without using labeled images and just by using the common sense, because the labeled images are just there to compensate for many facts that we don't know about, together with learning visual representations for the backbone. We can use the representation for the backbone using a self-supervised approach, such as bootstrap your own latent, where we don't really need labels. On the other hand, if you just have a form of knowledge, such as a woman riding a horse, man riding a horse, and triples in form of general knowledge, we can fine-tune the rest of the network from this knowledge and then use this knowledge in order to improve our classification with much less data. And as I showed, we use 1% or 10% of the data and get still very good classification results. In order to do that, I will, there's an echo. I will try to, I'm not sure how to. Maybe I reduced the volume of the microphone. Sorry. Oh, no, actually, it's kind of okay. Yeah, there's not much else I can do. I hope. Oh, okay. All right. Everybody else is all right. Sorry then. I will continue. So in order to do that, I will introduce a form of representations which we call schema representations. This is inspired by a prior work of Jean Piaget in 1900s. And then I will show that in the results, we can improve the classification in normal inference, and we can improve the classification in training by using only 1% or 10% of the classifications. And the improvements are quite significant in this case. First, I will motivate the work by related works because they're relevant in understanding the work better. Let's say we are given an input image and we have classified it. How can we correct our classification? For example, let's say we haven't been able to classify the bull, or we have just misclassified it to a different class. What we can do is we can just go to a form of like a prior model that we can just build probabilistically from all the knowledge in the world that tells us that, yeah, fruits can be in the bowl. This probabilistic knowledge can help us to be compared to the initial classification results here, and then further correct them. However, the problem that this form of classification has is that it doesn't generalize. For example, if you know that fruits go into the bowl, but you have never seen a fact explicitly that says also oranges go into bowls, then you cannot really generalize to this fact, and you wouldn't know this fact. However, what you can do is you can build a knowledge graph embedding model, and knowledge graph embedding models can help you generalize. How do they do that? Usually in knowledge graph embedding models, you take a fact, and instead of having like just a symbolic one-hot vector, such as in a symbolic knowledge graph itself, we assign it a vector. And then we capture the interaction between two vectors, between two different entities, such as orange going into the bowl and fruits going into the bowl, and we assign vector representations to each entity. When we look at the training data and we train and find such embeddings, the embeddings for similar entities fall in the similar, like nearby parts of the space. So if we have never seen a woman riding a horse, if you have never seen a man riding a camel, but we have seen a woman riding a horse, we can generalize to this fact because we know that man and woman are similar to each other because their embeddings are similar to each other, and horse and camel are also similar to each other. Therefore, knowledge graph embedding models can help us to further improve the previous model. What is still missing here is that this prior model that we just described here and the perception model that we had in the beginning, they're totally separate from each other. They're trained separate from each other. They don't know anything about each other. The problem then is that, let's say in our symbolic facts, we have actually never seen that a man rides a camel. But if we have previously looked at the images, we could have detected that actually camels and horses kind of look similar. They both have four legs and so on. So visually, we could generalize to the fact that a man can also ride a camel. And this is the thing that we do in this work. And we kind of entangle the perception and the prior into the same model, such as it was similar to what Piaget was proposing. This, of course, has the highest generalization capability among the other models. I will give a brief background now. So, like a convolutional neural network can extract image-based representations when we feed it with an image. On the other hand, we can have symbol-based representations. For example, what is a representation for an apple, or what is a representation for a man? We can see here that Da Vinci had a drawing of the Vitruvian man. And in this drawing, he was actually drawing the theory of forms, which Plato talked about a long time ago. And in theory of forms, Plato said that every human being has access to a form of perfect representation for every entity. Each of us has a representation for the perfect man or the perfect apple, and so on, in our mind. And he believed that we use this to live in the world. However, later, Jean Piaget, and by later I mean just like 100 years ago, Piaget was a cognitive psychologist. He said, well, we are not, like, there is no perfect representation that we have access to from a spiritual realm of forms, but instead we actually learn these representations during the perceptions that we have in our lifetime. For example, the representation of a man in my mind is different than the representation of a man in your mind, because you have seen different men in your life, or different apples in your life. And the symbolic canonical representation for these entities are depending on what we have seen. So this was symbol-based. This was learned from prior perception, and it lies in some sort of latent space because it's not necessarily in the pixel space, right? And it also has compositionality. So if we know a man can ride a horse, a woman can ride a horse, and we can have different compositions of that. Given this knowledge, I'm going to now talk about the architecture and how we use this understanding in order to improve the perception, given these prior perceptions that we can learn throughout our lifetime, basically. So let's say we're given an image, we feed it to a typical CNN, and we extract different entities out of it. And these entities, each of them have a representation. So these red, blue for the nodes, which are representing the objects, they are basically some sort of embedding, pulled from the convolutional neural network. And for the edges, what we have is the spatial vector that captures the 2D relation between different entities in the image. In this case, it's 2D because we just work with images, but it could be 3D, of course. And as this is the XI, which is the image-based representations. Then we feed them to a graph transformer, basically to just do a message propagation such that each neighbor can be made aware of each other. This could be other forms of message propagation, but graph transform showed the best results for us. And we extract ZIs, basically, which we call contextualized representations. The ZIs are kind of still focused on the main objects, but it's neighbor aware. So the man knows that in the image there are other entities too, because before it was not fully aware of necessarily. The conv layers kind of merge stuff up to a point, but not necessarily. What we have now is actually, here you need to pay a bit more attention, because what happens now is not an addition part of the feed-forward network, but the feed-forward network finishes here. We have extracted the representations, and now we want to classify the representations as a first step. For classification, we can have each node representation or each edge representation attend to a full list of different possible nodes, which are our different possible classes. These are what we call our schema representations, or SIs, where if you look at it, it is basically what's happening in the typical classification layer of a normal network. But the change comes now. Once we define it as an attention layer, we don't just use the attention coefficients, which are the result of the softmax operation there, which show what is the similarity of this node to all the possible nodes, but we actually take the representation of the schema and we propagate it back. This means that if we have detected that one part of the network is a man, then we can take the representation, the schema of a man, and keep it here together with the actual image-based representation of the man. In next steps, we can propagate again, and this process repeats again and again, such that the neighbors are made aware of each other's canonical representations, which is now not just the image-based noisy representation, but the actual canonical representation that can store the prior knowledge about different entities. So it's important to note that actually the schema representation also can give us a form of probabilistic knowledge graph about the whole possible facts and the possibility of different facts that happen in the world. How can we do that? What we can do is we can set the node representations that come from the image to just the zero vector. So we don't care about them. Now we want to make a query. We want to say, well, what does the man write? So we can activate the node of man here and the node of writing here, and we can feed them through the network as if there's no images. And then it can give us a probability of like horse or anything else. This is similar to humans, right? Like if you can look at an image, I can ask you what is in the image, and you can tell me there's a man or there's a riding horse, or you don't have to look at the image. I can just tell you, what do you think a man can ride? And you can query your semantic knowledge and basically tell what's happening there. These are all inspired also by the processes in the semantic memory, which we do not discuss explicitly in this paper actually, but we have another paper on the connection between semantic memory, episodic memory, and perception, which if you're interested, you can check it in my Google Scholar. It's not finalized yet, there are different versions, but in general, it's called the tensor brain theory. Each step so we can do this recurrent step several times. Each step is called one assimilation. This is also a terminology inspired by prior works of Piaget. Okay, yeah, this is where I was talking about. We can just set the x to 0. All right, I'm going to move into the evaluation results. So we did the experiments with the visual genome data set. And in visual genome, some of you might be familiar. There's several objects in an image, and in general, there are 150 object classes, and there are 50 predicate classes. Predicates are basically the relations. And then there are different settings to evaluate, like scene graph classification, where we have to evaluate how good we can classify both objects and the relations in an image, and the predicate classification, where we can evaluate how well we can classify just the relations, because that's important on itself for the community. And there's the constrained and unconstrained setups. I'm not going to go through all the details, but you can ask me if in the tables something was unclear. We use the VGG16 backbone for the supervised setups, and we use ResNet 50 so that we can just use the out-of-the-box bootstrap your own latent or BU network as the self-supervised backbone. Yep. Oh, so I might sometimes be referring to backbone. That's just basically these two. And sometimes I talk about main model. And by main model, I mean other parts of the network that apply the contextualization, the graph transform, and the assimilation, which is the recurrency. So the first step, as I discussed in the earlier in the talk, is schemata for inference. So we evaluate it, and we can see that every time that we propagate back this knowledge, when I say propagate back, please don't mistake it by back propagation of the gradients. This is propagation of the knowledge, and when I say back, it's because it goes back into the network. And then at each step, the accuracy improves. Of course, the first jump is always the best because it gives the most information. And we can see in qualitative results like what can happen. For example, on the top right image, we have a man riding a bike. The green represents what has been originally classified correctly. The gray represents what has been not classified correctly. For example, here, I remember it specifically that the sidewalk was originally classified as a street, but the original label is just a sidewalk. And you can see that the network goes through these images and said, okay, well, it looks like a man is riding a bike and a man is sitting on the chair. And then it starts thinking, but well, this cannot be a street, right? Because originally it looks like a street. But once you know that a man is sitting on a chair and a man is riding a bike, your common sense tells you that, well, this should be a sidewalk. I don't think this is a street. So you can correct your classification. The same happens to the other examples. For example, here we have a truck and there are 4 wheels, and you can look at the wheels, you classify some of them, but this last one at the corner is really not visible. So it's misclassified. But once you know that there's a truck, this helps us to look at the image again, this time with our common sense more involved, and know that the wheel is visible in the image. These are some examples, similar examples after 3 steps of assimilation where we can detect that the woman is sitting on the bench, and then the table is not detected, then the table is detected. Once the table is detected, the cup is easier to be classified, and so on. And we show that this improves the results compared to the previous works. Also, this is not like, if you have a question, I can get back to the slide. This is about the distribution of the improvement for each predicate, and the fact that it's not really overfitting, but it's really learning common sense, and it generalizes because the predicates that are happening mostly are not necessarily the ones that are improved, but others are also improved. In the second setting, we have the schemata for training, which I discussed earlier. In order to do this evaluation, we basically threw out 99% of the data, and we just used one of the images, for example, like out of 10, sorry, out of 100. And then we also had the 10% setting where we had 1 out of 10. And instead of using the images themselves, we basically used the knowledge that are in the annotation. So we throw away the images, but the images are annotated with the typical visual common sense. So they tell us that like there's an elephant on the grass, or I don't know, like other facts, like a person is eating in something. And we can use this fact to improve basically the schemata. If you remember the previous image that I showed you, you always set the images to 0 in this setting after pre-training the network, and then you fine-tune given the common sense that we have. I can imagine there might be questions actually about this part. If it's not clear, we can continue on that given the questions. In order to evaluate it, we had the supervised backbone with 1% or 10% of the labeled data. And we also had the self-supervised backbone. The reason to switch to the self-supervised backbone is because it's really hard to train like CNN with 1% of the data. Whereas if you use self-supervised without labels, we don't need the labels anymore, but we can have a very good backbone. If some of you are familiar with self-supervised methods, I think Ali talked about this earlier this week. They do magic basically in this case. So we use a self-supervised backbone. And then once we have this backbone, now we can use the external data in order to improve the main model. And we get significant improvement here, especially in predicate classification, where the accuracy when we use 1% of the data is almost the same as when we use 100% of the data. In predicate classification, I want to mention that this is about detecting really the relations. And this also gives us improvement in object classification or scene graph classification. It is less, it's more challenging, but there's still like good improvement here. Then we were curious, like, okay, what have the schemata actually learned? So we visualized the schemata with the CSNE, and you can see that, for example, yeah, the horse and the zebra and the cow, they all fall within the same category. So basically what happens is the entities that appear similarly or appear in similar relations, so either visually similar or relationally similar, they fall together and they can be clustered better together. And by injecting them back, these are the representations of the ZIs, basically. By injecting each time the prior knowledge back into the network, we get better clusterable clusters, basically, that can help us in the classification. And yes, then basically this can help us get quite good improvements. So yeah, and overall, I discussed the schemata as mental representations, kind of, that enable compositionality and reasoning, and by defining classification as an attention layer instead of just a typical fully connected layer, introduced this inductive bias that can enable learning and propagation of the prior knowledge. And as you could see in the experiments, we gained the improvement. Thank you very much.